Hello, my dear, and let's start our astronomy course. Today, we have lecture number 13, and we will be continuing study neutron star and black hole. Okay? So, your knowledge of pulsar suggests that newborn pulsar should blink very, very rapidly, and old pulsar should blink in opposite slowly. In fact, the handful that blink the fastest may be quite old. One of the fastest known pulsars is cataloged as 13 feet AD in the constellation Sagittarius. It pulses 716 times a second and is slowing down only slightly. The energy stored in the rotation of a neutron star at this rate is equal to the total energy of a supernova explosion. So it seems difficult at first to explain this pulsar. It now appears that 2005 AD is an all-neutron star that has gained mass and rotational energy from a companion in a binary system. Like water hitting a mill wheel, the matter falling on the neutron star has spun it up to 716 rotations per second. With its weak magnetic field, it slowed down very gradually and will continue to spin for a very long time. A number of other very fast pulsars have been found too. They are known generally as milliseconds pulsars because their pulse periods and therefore their periods of rotation are almost as short as a millisecond. It's look like 0.001. This rapid rotation produces some fascinating physics. If a neutron star 10 kilometers in radius spins 716 times a second, as does 5 AD, then its period is 0.0014 seconds. And the equator of a neutron star must be traveling about 45,000 kilometers per second. That is fast enough to flatten the neutron star into an ellipsoidal shape and is nearly fast enough to break it down. The fastest known pulsar, XTEJ 1739-285, spins 1,122 times a second. It appears to have been spun up by matter flowing from its companion star and is very near the breakup speed for an object composed of pure neutrons. All scientists should be made honorary citizens of Missouri, the show me state, because scientists demand evidence. The hypothesis that the millisecond pulsars are spun up by mass transfer from a companion star is quite reasonable. But astronomers, yes, correct, astronomers demand evidence. And evidence has been found. For example, the pulsar PSRJ 1740 and 55340 has a period of 42 milliseconds and is orbiting with a bloated red star from which it is gaining mass. This appears to be a pulsar caught in the act of being spun up to high speed. For another example, consider the X-ray source XTEJ1751 305, a pulsar with a period of only 2.3 milliseconds. X-ray observation shows that it is gaining mass from a companion star. The orbital period is only 42 minutes, and the mass of the companion star is only 0.014 solar mass. The evidence suggests this neutron star has devoured all but the last morsel of its binary path. Also, some milliseconds pulsars have binary companions, some are solitary neutron stars. A pulsar known as a black widow may reveal how a fast pulsar can lack of a companion. The black widow has a period of 1.6 milliseconds, meaning it is spinning 622 times per second, and it orbits with a low mass companion. Presumably, our neutron star was spun up by mass flowing from the companion. But spectra show that the blast of radiation and high energy particles from the neutron star is now boiling away the surface of the companion. The black widow has eaten its fill and is now evaporating the remains of its companion. It will soon be a solitary millisecond pulsar, as you can see in this slide. Show me, say scientists, and in the case of a neutron star, the evidence seems very strong. Of course, you can never prove that a theory is absolutely true. But the evidence for neutron stars is so strong that astronomers have great confidence that they really exist. Other theories that describe how they emit beams of radiation and how they form and evolve the less certain, but continuing observation at many wavelengths are expanding astronomers' understanding of these last embers of massive stars. In fact, precise observations have turned up objects no one expected. Because a pulsar's period is so precise, astronomers can detect tiny variations by comparing their observations with atomic clocks. When astronomers check pulsar PSR 1257 plus 12, they found variations in the period of pulsation much like those caused by the orbital motion of a binary pulsar, as you can see on the left part of this slide in figure A. However, in the case of PSR 1257 plus 12, the variations were much smaller. And when they were interpreted as Doppler shifts, it became evident that the pulsar was being orbited by at least two objects with planet-like masses of 4.1 and 3.8 Earth masses. The gravitational tuned task of this planet makes the pulsar wobble about the center of mass of the system by no more than 800 kilometers, producing the tiny changes in period. This you may see in the right part of this slide in figure B. Astronomers greeted this discovery with both enthusiasm and skepticism. As usual, they looked for ways to test the hypothesis. Simple gravitational theory predicts that planets in the same system should interact and slightly modify each other's orbit. When the data were analyzed, that interaction was found, further confirming the existence of the planet. In fact, later data revealed the presence of a third planet of about twice the mass of the Earth's moon. This illustrates the astonishing precision of studies based on pulsar time. Astronomers wonder how a neutron star can have planets. The three planets that orbit PSR 1257 plus 12 is closer to the pulsar than Venus is to the Sun. Any planet that orbited a star that closely would have been absorbed or even vaporized when the star expanded to become a supergiant. And furthermore, the supernova explosion would have suddenly reduced the mass of the star and allowed any orbiting planet to escape from their orbit. It seems more likely that these planets are the remains of a stellar companion that was devoured by the neutron star. In fact, PSR 1257 plus 12 spins very fast, 161 pulses per second, suggesting that it was spun up in a binary system. PSR 1257 plus 12 is not unique. Another planet has been found orbiting a neutron star that is part of a binary system with a white dwarf. Because this system is located in a very old star cluster and contains a white dwarf, astronomers suspect that the planet may be very old. Planets probably orbit other neutron stars, and small shifts in the timing of the pulses may eventually reveal their presence. You can imagine that this world might be life, formed from the remains of elderly stars. They might have chemical compositions richer in heavy elements than Earth. You can imagine visiting this world, landing on their surfaces, and hiking across their valleys and mountains. Above you, the neutron star would glitter in the sky, a tiny point of light. And now we have another scientific argument. Why are neutron stars easier to detect at X-ray wavelength? This argument draws together a number of ideas you know from previous lectures. And first, recall that a neutron star is very hot because of the heat released when it contracts to the radius of only 10 kilometers. It could easily have a surface temperature of 1 million Kelvin. And Wien's law tells you that such an object will radiate most intensively at a very short wavelength, namely in X-ray. Normal stars are much cooler and emit only weak X-rays unless they have hot accretion disks. At visual wavelength, stars are bright and neutron stars are faint, but at X-ray wavelength, the neutron stars stand out from the crowd. Now build a new argument, as if you were seeking funds for a research project. What observation would you make to determine whether a newly discovered pulsar was young or old, single or member of binary system, alone or accompanied by the planet? How this interesting. And now let's begin to the next part of our lecture, black hole. You have now studied white dwarfs and neutron stars, two of the three and state of time stars. Now it's time to think about the third and state, black hole. Also, the physics of black holes is difficult to discuss without using sophisticated mathematics. Simple logic is sufficient to predict that they should exist. The problem is to confirm that they are real. What object observed in the heavens could be real black hole? More difficult than the search for neutron stars, the quest for black holes has nevertheless met with success. To begin, you must consider a simple question. How fast must an object travel to escape from the surface of a celestial body? Suppose you threw a baseball straight up. That's very popular in USA. How fast must you throw it if it is not to come down? Of course, gravity will always pull back on the ball, slowing it, but if the ball is traveling fast enough to start with, it will never come to a stop and fall back. Such a ball will escape from Earth. In previous semester, you learned that the escape velocity is the initial velocity an object needs to escape from a celestial body. Let's look at this slide. Whether you are discussing a baseball leaving Earth or a photon leaving a collapsing star, escape velocity depends on two things: the mass of the celestial body and the distance from the center of mass to the escaping object. Are you agree with me? Nice. If the celestial body has a large mass, its gravity is strong, and you need a high velocity to escape. But if you begin your journey farther from the center of mass, the velocity needed is less. For example, to escape from Earth, a spaceship would have to leave Earth's surface at 11 kilometers per second. But if you could launch spaceships from the top of a tower 100 miles, not 100, even thousands miles high, the escape velocity would be only 10 kilometers per second. If you would make an object massive enough or small enough, its escape velocity could be greater than the speed of light. Relativity says that nothing can travel faster than the speed of light. So even photons, which have no mass in the rest, would be unable to escape. Such a small, massive object could never be seen because light would not leave it. Another interesting topic today is Schwarzschild black hole. If the core of a star contains more than 3 solar masses when it collapses, no force can stop it. It cannot stop collapsing when it reaches the density of a white dwarf, because degenerate electrons cannot support the weight. And it cannot stop when it reaches the density of a neutron star, because not even degenerate neutrons can support the weight. So no force remains to stop the object from collapsing to zero radius. As an object collapses, its density and the strength of its surface gravity increases. And if an object collapses to the zero radius, its density and gravity become infinity. Mathematicians call such a point of singularity. But in physical terms, it is difficult to imagine an object of zero radius, right? Some theorists believe that a singularity is impossible, and that the laws of quantum physics must somehow halt the collapse at some subatomic radius roughly 1,020 times smaller than a proton. Astronomically, it seems to make little difference. If the contracting core of a star becomes small enough, the escape velocity in the region of space around it is so large that no light can escape. And this means you can receive no information about the object or about the region of space near it, because it emits no light. Such a region is called, namely, black hole. If the core of an exploding star collapsed in a black hole, the expanding outer layers of the star could produce a supernova enough, but the core would vanish without a trace. To understand black holes, you must consider relativity. In 1916, Albert Einstein published a mathematical theory of space and time that became known as the general theory of relativity. Einstein treated space and time as a single entity called space-time. His equation showed that gravity could be described as a curvature of a space-time. And almost immediately, the astronomer Karl Schwarzschild found a way to solve Einstein's equations to describe the gravitational field around a single, non-rotating electrically neutral lump of matter. That solution contains the first general relativistic description of a black hole. And non-rotating, electrically neutral black holes are now known as Schwarzschild black holes. In recent decades, theorists such as Roy Kerr and Stephen Hawking have found ways to apply the sophisticated mathematical equations of the general theory of relativity and quantum mechanics to charge rotating black holes. For this discussion, the differences are minor, and you may proceed as if all black holes were Schwarzschild black holes. Okay? Schwarzschild's solution shows that if matter is packed into a small enough volume, then space-time curves back on itself. Objects can still follow paths that led into the black hole, but no path leads out. So nothing can escape, because not even light can escape. The inside of the black hole is totally beyond the view of an outside observer. The event horizon is the boundary between the isolated volume of space-time and the rest of the universe, and the radius of the event horizon is called the Schwarzschild radius. Here we have as R sub S, Schwarzschild radius. A collapsing stellar core must shrink inside its Schwarzschild radius to become a black hole, as you can see in this slide. Also, Schwarzschild's work was highly mathematical, and his conclusion is quite simple. The Schwarzschild radius in meters depends only on the mass of the object in kilograms, as you may see on this slide. In this simple formula, G capital here is the gravitational constant, M capital is the mass, and C is the speed of light. A bit of arithmetic shows that one solar mass black hole has a Schwarzschild radius of only 3 kilometers. A 10 solar mass black hole has a Schwarzschild radius of 30 kilometers, and so on. Even a very massive black hole would not have a very large event horizon. Every object has a Schwarzschild radius determined by its mass, but not every object is a black hole in reality. For example, Earth has a Schwarzschild radius of about 1 centimeter, only was size very small. But it could become a black hole only if you squeezed it inside that radius. But in reality, it's impossible. Fortunately, Earth will not collapse spontaneously to become a black hole because the strength of the rock and metal in its interior is sufficient to support its weight. Only exhausted stellar core, more massive than about 3 solar masses, can form black holes under the sole influence of their own gravity. It is a common misconception to think of black holes as giant vacuum cleaners that will eventually suck in everything in the universe. A black hole is just a gravitational field, and at a reasonably large distance, its gravity is no greater than that of a normal object of similar mass. If the sun were replaced by a 1 solar mass black hole, the orbit of the planet would not change at all. And this figure illustrates this by representing gravitational field as curvature of the fabric of space-time. Normal, uncarved space-time is represented by a flat plane and the presence of a mass, such as a star carve the plane to produce the depression. The extreme curvature around a black hole produces a deep tunnel-shaped surface in this graphic representation. You can see from the graph that the gravity of a black hole becomes extreme only when you approach close to it. Now you can check off another common misconception that may strike you as silly. Because of special effects in movies and TV, some people think black holes should actually look like funnels. Of course, the graph of the strength of gravity around black holes look like funnels. But black holes themselves are not shaped like the funnel. If you could approach a black hole, you might be able to see hot gas whirling inward, but you wouldn't be able to see the black hole itself. Before you can search for real black hole, you must understand what theory predicts about a black hole. To explore that idea, you can imagine leaping feet first into a Schwarzschild black hole. If you were to leap into a black hole of a few solar masses from a distance of an astronomical unit, the gravitational pull would not be very large, and you would fall slowly at first. Of course, the longer you fell and the closer you came to the center, the faster you would travel. Your wristwatch would tell you that you fell for about 2 months by the time you reach the event horizon. Your friend who stayed behind would see something different. They would see you falling more and more slowly as you came closer to the event horizon. Because, as explained by general relativity, time slows down in curved space-time. This is known as time dilation. In fact, your friends would never actually see you cross the event horizon. To them, you would fall more and more slowly until you seemed hardly to move. Generalization later, your descendants would focus their telescope on you and see you still inching closer to the event horizon. You, however, would have sensed no slowdown and would conclude that you had reached the event horizon after about 2 months. Another relativistic effect would make it difficult to see you with normal telescope. As light travels out of gravitational field, it loses energy, and its wavelength grows longer. This is known as the gravitational redshift. Also, you would notice no effect as you fell towards the black hole. Your friends would need to absorb a longer and longer wavelength in order to detect. While these relativistic effects seem merely peculiar, other effects would be quite unpleasant. If you were falling feet first, you would feel your feet, which would be closer to the black hole, being pulled in more strongly than your head. And this is a tidal force. And at first it would be minor. But as you feel closer, the tidal force would become very large. Another tidal force would compress you as both your left and your right side fell toward to the center of the black hole. For any black hole with a mass like that of a star, the tidal forces would crush you laterally and stretch you longitudinally long before you reach the event horizon. Let's look at this slide in picture fashion. The friction from such severe distortion of your body would hit you to millions of degrees, and you would emit X-rays and gamma rays. Do black holes really exist? The first X-ray telescope reached orbit in the 1970s, and that allowed astronomers to begin searching for evidence of the black hole. They tried to find one or more objects. They were obviously black holes. That very difficult search is a good illustration of how the unwritten rules of science help scientists understand nature. A black hole alone is totally invisible because nothing can escape from the event horizon. But if matter flows into a black hole, the matter will become very hot and can emit X-rays before it reaches the event horizon. An isolated black hole in space will not have much matter flowing into it. But a black hole in a binary system might receive a steady flow of matter transferred from the companion star. And this suggestion can search for black holes by searching among X-ray binaries. Some X-ray binaries, such as Hercules X1, contains a neutron star, and they will emit X-rays much as would a binary containing a black hole. You can tell the difference in two ways. If the compact object emits pulses, you know it is a neutron star. Otherwise, you must depend on the mass of the object. If the mass of the compact object is greater than 3 solar masses, it cannot be a neutron star because it must be a black hole. The first X-ray binary suspected of harboring a black hole was Cygnus X1, the first X-ray object discovered in Cygnus. It contains a supergiant binary object B0 star and a compact object orbiting each other with a period of 5.6 days. Astronomers suspected that the X-rays were emitted by matter from the star, flowing into the compact object. The object is invisible, but Doppler shifts in the spectrum reveal the motion of the B0 star around the center of mass of the binary. From the geometry of the orbit, astronomers were able to calculate that the mass of the compact object had to be greater than 3.8 solar masses, well above the maximum for a neutron star. To confirm that black holes existed, astronomers needed a conclusive example, an object that couldn't be anything else. Cygnus X1 didn't quite pass the test when it was first discovered. Perhaps the B0 star was not a normal star, or perhaps the system contained a third star. Either possibility would distort the analysis. At the time, astronomers could not conclusively show that Cygnus X1 contained a black hole. It took years of work to understand Cygnus X1. Further observations and analysis show that the star has a mass of about 25 solar masses, and the compact object is about 10 times the mass of the Sun. Astronomers conclude that matter flows from the B0 star as a strong stellar beam, and much of that matter gets caught in a hot accretion disk, about 5 times larger in diameter than the orbit of the Earth moon. The inner few hundred kilometers of the disk has a temperature of about 2 million Kelvin, hot enough to radiate X-ray. The evidence is now strong that the Cygnus X1 contains a black hole. As X-ray telescopes have found many more X-ray objects, the list of black hole candidates has grown to dozens. A few of these objects are shown in this table. Such candidate is a compact object surrounded by a hot accretion disk in a closed X-ray binary system. Some of the binary systems are easier to analyze than others, but in the end, it has become clear that some of these objects are too massive to be neutron stars and must be black holes. Another way to confirm that black holes are real is to search for evidence of their distinguishing characteristic, event horizon. And that search too has been successful. In one study, astronomers selected 12 X-ray binary systems, 6 of which seemed to contain neutron stars, and 6 of which were thought to contain black holes. Using X-ray telescopes, the astronomers monitored the system, watching for telltale flares of energy as blobs of matter fell into the accretion disk and spiraled inward. In the 6 systems thought to contain neutron stars, the astronomers could also detect bars of energy when the blobs of matter finally fell onto the surface of the neutron star. In the 6 systems suspected of containing black holes, however, the blobs of matter spiraled inward through the accretion disk and vanished without final bars of energy. Evidently, those blobs of matter have vanished as they approach the event horizon. Please look at this picture. This is a dramatic evidence that event horizons are real. The evidence shows that black holes really do exist. The problem now is to understand how these objects interact with the matter flowing into through accretion disks to produce high energy jets and outbursts. Let's come to the next scientific argument. If realistic effects slow time and prevent you from seeing matter cross the event horizon, how can infalling matter disappear without a trace? This argument brings together observations and theory. Astronomers saw flares when matter hit the surfaces of neutron star, but saw nothing but matter fell into a black hole. Also, time slowed near the event horizon. Remember the gravitational redshift. Okay? Hot matter flowing into a black hole and can emit X-ray. But as the matter near the event horizon, the gravitational redshift lengthens the wavelength dramatically. The matter vanished, not because you see it cross the event horizon, but because its photons are shifted to undetectable long wavelengths. How build a new argument to review a basic principle. And now, why does matter become hot as it spirals into a black hole? How do you see? I'm interested in your. Now, let's start another subtopics today's lecture. Compact objects with these ends hole. So, matter flowing into a neutron star or a black hole forms an accretion disk. And that can produce some surprising phenomena. Astronomers are just beginning to understand these particular effects. Observations show that some compact objects are emitting jets of gas and radiation in opposite directions. These jets are similar to the bipolar outflow ejected by protostars, but much more powerful. You have seen in the X-ray images that show that some young pulsars, including the Crab Nebula pulsar, are ejecting jets of high excited gas. The Vela pulsar does the same, as you look in this picture. Systems containing black holes can also eject jets. The black hole candidate J165540 has been absorbed at radio wavelength, sporadically ejecting oppositely detected jets at 92% of the speed of light. One of the most powerful examples of this process is an X-ray binary called SS433. Its optical spectrum shows sets of spectral lines that are Doppler shifted by about 1/4 of speed of light. This one set shifted to the red and one set shifted to the blue. And furthermore, the two sets of lines shift back and forth across each other with a period of 164 days. At the time of its discovery, news media reported with a smear that astronomers had discovered an object that was both approaching and receding at fantastic speed. But astronomers recognized the Doppler shift as evidence of oppositely directed jets. Apparently, SS433 is a binary system in which a compact object, probably black hole, pulls matter from its companion star and forms an extremely hot accretion disk. Jet of high temperature gas blast away in beams aimed in opposite direction. As the disk processes, it sweeps these beams around the sky once every 164 days. And telescopes of Earth detect light from the gas carried outward in both beams. One beam produces a red shift, and the other produces a blue shift. It's not clear how the accretion disk can produce jets. Accretion disks around neutron stars and black holes are very small, spin very fast, and grow very hot. Somehow the hot gas in the disk can emit powerful beams of gas and radiation. along its axis of rotation. The exact process isn't well understood, but it seems to involve magnetic fields that get caught in the accretion disk and are twisted into tightly wound tubes that squeeze gas and radiation out of the disk and confine it in narrow beams. You can recognize the geometry of SS-433 in this figure. Yes? Such pair of jets are prototypes that illustrate how the gravitational field around a compact object can produce powerful beams of radiation and matter. You will meet this phenomenon again when you study peculiar galaxies in a later lecture. And now let's begin to gamma ray bursts. The Cold War plays a minor part in the story of neutron stars and black holes. In 1963, a nuclear test ban treaty was signed, and by 1968, the United States was able to put a series of satellites in orbit to watch for the nuclear tests that were violation of the treaty. The nuclear detonation emits gamma rays, so the satellites were designed to watch for bursts of gamma rays coming from Earth. The experts were startled when the satellite detected about 1 gamma ray burst a day coming opposite side from space. And when those data were finally declassified in 1973, astronomers realized that the bursts might be coming from neutron stars and black holes. These bursts are now known as gamma ray bursts. The Compton Gamma Ray Observatory reached orbit in 1991 and immediately began detecting gamma ray bursts at the rate of a few a day. Its observations showed that the intensity of the gamma rays rises to a maximum in seconds and then fades away. A burst is usually over in a few seconds to a minute. Data from the Compton Observatory also showed that the gamma ray bursts were coming from all over the sky and not from any particular region. And this helped astronomers eliminate some theories. For example, some theories held that the gamma ray bursts were being produced by relatively common events involving the stars in our galaxy. But the result from the Compton Observatory eliminated that possibility. If the gamma ray bursts were produced among stars in our galaxy, you would expect to see them most often along the Milky Way, where there are a lot of stars, right? That the bursts occurred all over the sky means that they were being produced by rare events in distant galaxies. Gamma ray bursts are hard to study because they occur without warning and fade so quickly. But starting in 1997, new satellites in orbit were able to detect gamma ray bursts. Such studies showed that there are two kinds of gamma ray bursts. Short bursts last less than 2 seconds, but longer bursts can go on for many seconds. Specialized satellites who detect bursts quickly determine their location in the sky and immediately alert astronomers on the ground. When telescopes on Earth swivel to image of location of the burst, they detected fading globes that resembled supernovae, suggesting that long gamma ray bursts are produced by a certain kind of supernova explosion. Theory proposed that a star more massive than some upper limit of about 20 solar masses can exhaust its nuclear fuel and collapse directly into a black hole. Models show that the collapsing star would conserve angular momentum and spin very rapidly, slowing the collapse of the equatorial part of the star. The poles of the star would fall in quickly, and that would focus beams of intense radiation and ejected gas that would blast out along an axis of rotation. Such an eruption has been called a supernova. If one of those beams were pointed at Earth, it could produce a powerful gamma ray burst. The evidence seems clear that the long gamma ray bursts are produced by hypernovae. Short gamma ray bursts don't seem to be associated with hypernovae. Some repeat, and these repeating bursts seem to be produced by neutron stars with magnetic field 100 times stronger than that in a normal neutron star. Double magnetized. This object can produce bursts of gamma rays when shifts its magnetic field break the crust of the neutron star. One of these objects produces a burst of gamma rays that reached Earth on August 27, 1998, and temporarily ionized Earth's upper atmosphere, disrupting radio communication worldwide. Internet at that time was only in a beginning, so not too many people taking into account this effect. Not all short gamma rays bars are produced by magnetars. Some bars have occurred in parts of distant galaxies where you would not expect to find the young, massive stars that produce magnetar or hypernovae. And the afterglows don't resemble fading supernovae. These bars may be produced by the merger of two neutron stars that orbited around each other, radiated orbiting energy as gravitational radiation, and spiraled into each other. The catastrophic merger would produce a violent explosion as the two neutron stars merged to form a black hole. Some other short gamma rays bursts are evidently produced by the merger of a neutron star and black hole. As these objects spiral into each other, the neutron star is ripped apart and swallowed by the black hole. That could produce a gamma ray burst, but the burst and its fading afterglow should be different from that produced by the merger of two neutron stars. Astronomers are now working to distinguish between these two kinds of short gamma ray bursts. The brightest gamma ray burst ever recorded occurred on March 19, 2008. It originated in a galaxy 7.5 billion light years from Earth, but it was so powerful that for about 1 minute it was bright enough to see with the unaided eye. No one knows what caused that burst, but it is clear that gamma ray bursts are among the most powerful events in nature. A nearly binary pulsar is only 1,600 light years from Earth. If a gamma ray burst occurred at this distance, the gamma rays would shower Earth with radiation equivalent to a 10,000 megaton nuclear blast. The largest bombs ever made were a few megatons for comparison. The gamma rays could create enough nitric oxide in the atmosphere to produce intense acid rain and would destroy the ozone layer and expose life on Earth to deadly levels of solar ultraviolet radiation. Gamma ray bursts can occur relatively near the Earth as often as every few hundred million years and could be one of the causes of the mass extinction that show up in the fossil record. Does it surprise you that such rare events as merging neutron stars and hypernova produce something so common that gamma ray telescopes observe one or more every day? Remember that these events are so powerful and they can be detected over very great distance. These may be these sorry maybe 30,000 neutron star binary in each galaxy, and there are billions of galaxies within range of gamma ray telescope. I think it's enough for today, and I hope you enjoyed this lecture as usual. And moreover, I am looking forward to seeing you next time. Bye.